Morning. Testing. All right, sounds good. All right, hey everyone. My name's Samuel Bennett, and with on this stream, I'm going to be streaming the development of a like rendering engine in Haskell and Vulkan. So yeah, we'll be going over that from scratch. This is the second stream. You can watch the previous stream on my YouTube channel, which is it's youtube.com/sam_tv. It's at sam_bennett_tv. Here we go. So you can watch the previous stream, and I'll be uploading this stream as well. If you want to catch up. So in the last stream, we created a window, we initialized the Vulkan context, and then we started working on the swap chain. And I thought to start this stream, we might have a look at resource management in Haskell. Just a little quick primer on resource management because it's something that we're going to be doing a lot. Test. Great. All right. Let's get rid of. Just set this up. Just preparing some of this stuff so it's more entertaining to watch. All right, so in other languages like C++, you have your like constructors and destructors, and the destructor gets called, whenever an exception is called or the program finishes or blah blah. And we don't have exactly the same concept in Haskell. So imagine we have a resource that we want to acquire and free. So when you open a file, you should close the file when you're done. So here I've just got two functions that are approximating, or they're just proxying the acquisition and freeing of resources. So we might start with this idea of acquiring a resource, doing some work, and then freeing the resource like this. So if we were to execute this, it's a little bigger. So if we were to execute test one, you can see that we acquire a resource, we do some work, and then we free it. And that's all good. But what if an exception occurred here? Would we free the resource? So we acquire the resource, we start doing some work, and then there's an exception. And we don't free the resource. So that's a problem. So one of the patterns that we employ here is that we use this kind of like, it's like the with pattern. See it in lots of Haskell libraries. So what we do is that we ask the user to provide us the some work function. So we ask them to provide us with a function that is the work that they're going to do with the resource. What we do is that we acquire the resource, we start the some work function that the user's provided, then we catch any exceptions that occurred during that, if there are any, and if there is an exception, we free the resource, and then we make sure to rethrow the exception. And if there's not any exceptions, we free the resource. So if we were to use this, so some resource one, and then we were like, gave it an argument like doing some work, you can see that we acquire the resource, we do some work, we free the resource. And if we introduce an exception in here, you can see that we still acquire the resource, do some work, and free the resource. So we've got exception safety there, which is great. That's what we want. Now, this, we already have access to a function that'll do this for us. Like we don't have to write this kind of wordy block. It's called onException, and it will do exactly the same thing. So it'll do some work, and if there's an exception, it'll free the resource. And notice that because this catch statement rethrows the exception, we don't reach this free. So we're not going to double free in the case of an exception. And that's true here as well. If an exception occurs in some work, we'll free the resource and then rethrow the exception, and we won't reach this free. So we won't get double free behavior. So I'll just demonstrate that with resource 2 is exactly the same. So even though we're doing some work and throwing an exception, we acquire the resource, we do some work, and then we free it. So we're still good. But this exception here is known as a synchronous exception. And this is the kind of exceptions that you usually think about, you'd be familiar with. But there are also things in Haskell called asynchronous exceptions. And these are the exceptions that are thrown if you're running on a different thread and then your thread is killed, and an asynchronous exception is thrown. And if you're running a program and then the user control sees it, so interrupts it, an asynchronous exception is thrown. And the problem with asynchronous exceptions is like you don't know when they'll be thrown. They're not associated with a piece of work in your program. So for example, an asynchronous exception might be thrown in between these two lines. So after we acquire, and then before we do some work, we might get an asynchronous exception. And that's a big problem because we haven't installed an exception handler here. So we'll never reach our free. And to demonstrate that, I've got a little bit of a helper function here. And what it does is it calls one of our with functions with some work, and it introduces like a tiny bit of delay, and then it kills the thread. And what I'm going to do here is create a new with resource function that's going to delay after the acquire for a fair amount of time. What that's going to simulate is that we know that the asynchronous exception is going to hit here. So if we run async exception with resource 3, and then we do some work, you can see that we acquired the resource, we didn't reach doing some work, and we didn't free. So that's a problem. So there's this function called mask. Now I'm using this function called uninterruptible mask here at the moment. You can think of them as the same thing, and I'll explain why I'm using uninterruptible mask in a moment. But there's a function called mask, and what that does is it masks asynchronous exceptions in the block. So in the block of code passed to mask, asynchronous exceptions won't be able to interrupt. So asynchronous exceptions by default will just interrupt, but mask, what it does is it switches that block from being interrupted by asynchronous exceptions to polling for asynchronous exceptions. So it can look for asynchronous exceptions, but only when it wants to, which lets you manage when you're vulnerable. So in this case, we have the same thing as with resource 3, where we've got this kind of artificial delay here, and we know that the asynchronous exception is going to hit here. But what we're hoping is that with uninterruptible mask, the asynchronous exception will hit here, be ignored or buffered until later. We'll do some work, and then we'll free the resource if there's an exception or not. So let's try that. So we're going to use with resource 4. I'm going to do some work. So you can see that we acquired the resource. There's a bit of a delay. That's when the asynchronous exception would have hit. We do some work and we still free the resource. So that's great. We've got kind of asynchronous exception safety. But there's a bit of a problem with this code, is that if sorry, give me a sec. If an asynchronous exception hits not while we're delaying, but while we're doing work, it won't be handled. So the user might be expecting that the asynchronous exception behavior is just as it always is. So they've written some function and they're expecting the asynchronous behavior to be as it always is. So let's say they're going to thread delay instead of us. So what is that? 1, 2, 3, 4, 5, 6, 7. So they've done some thread delay and they're expecting that any asynchronous exceptions will interrupt their computation. What they'll find is that, oh, actually, let's make sure to reload this because I changed this function. What they'll find is that their computation isn't interrupted. So an asynchronous exception is hitting during their computation, but nothing's happening from their perspective, which is not what you want. So we've effectively, they've written some code expecting the asynchronous exception behavior to be a certain way, and we've switched that on them, which isn't ideal. So mask, it comes with a argument called restore, which lets us restore the default asynchronous exception behavior for that block of code. So here we go. With resource 5, we've got our mask, we've got restore, and we've restored the normal asynchronous exception behavior during the computation that the user has passed to us. So can demonstrate that with resource 5. So again, we're delaying during the user's computation, and the asynchronous exception is going to hit there, and we expect our resource to be freed and their computation to be interrupted. And there we go. So they didn't actually get to doing some work because the delay happened and then the asynchronous exception hit before they did their print statement. But we still acquired and freed the resource. So this is kind of like the optimal behavior. The asynchronous exception state is behavior is just as the user expects, and we're making sure to acquire and free the resource appropriately. So the reason I used uninterruptible mask here, and you usually wouldn't use uninterruptible mask, is because in Haskell, certain operations, such as thread delay, are marked as interruptible anyway. So if you were to mask, if we were to mask this computation, like let's change this to just the normal mask. And we were to say thread delay here. Let's make sure we just use the same amount. Then we were to try this again. So with resource 4, no delay on the user's computation. So what are we expecting to happen here? We're expecting the asynchronous exception that hits here to be ignored or buffered until later because we've got the mask on. And let's see if that's true. So it's not. The asynchronous exception hit during the delay and we didn't free anything, which what confused me. So this is because certain computations like thread delay, and basically any sort of like IO computation that is expected to take a long time or could take a long time, they're sort of marked as interruptible anyway. So even if you mask except asynchronous exceptions during that period, during that computation, the asynchronous exceptions will still get through, which is a little bit confusing. But the reason for that is like um, what you don't want happening is you're writing a program and then it hangs on some IO operation like this, like thread delay or opening a large file, and the user's like, oh, stuff this. I'm going to control C and interrupt this computation. You want that computation to be interrupted. Whereas if you're using an uninterruptible mask, that computation can't be interrupted, which means that from the user's perspective, the program will just hang and they won't be able to do anything about it. So that's why Haskell takes that approach. I'm sure there are other reasons too. That's what I know. Um, so I'm using uninterruptible mask here just so that I can demonstrate this idea, like I can show you, predict where the asynchronous exception is going to be thrown. But it's just something to keep in mind when you're writing your programs. So when it comes to asynchronous exceptions, what we're really thinking about is like, instead of just seeing these statements as like three separate statements, we're thinking about the spaces in between as well. Thinking like, okay, what if we acquire a resource and then an asynchronous exception is thrown here? Will I free the resource? It's like, well, no. That's why we add this mask here. That mask, it switches to polling mode for asynchronous exceptions. So if an asynchronous exception is thrown here, nothing will happen right now. We'll do some work, non-exception free, and then we'll free. And then when we exit the mask, the asynchronous exception will be thrown because it's kind of just waiting in a buffer. It doesn't disappear because we've masked. It's just going to wait there. And what we can do is restore the normal asynchronous exception behavior handling for a period of time, which means that if an asynchronous exception is thrown here, when we restore, it'll show up here because it's been buffered by this mask. But because we've restored the normal behavior, the buffer is the floodgates are opened. So yes, and let's get rid of this uninterruptible mask now because we're going to be using just mask. You rarely want uninterruptible mask. It's just that I wanted it to demonstrate. This is how this function here, this pattern is known as like the bracket pattern. So there's a function called bracket. And you can see bracket, you give it a computation to run first, acquiring the resource, a computation to run last, which is releasing the resource, and then a computation to run with the resource. That's where that with word comes from. So if we look at the implementation of bracket, you'll see it's pretty much exactly what we had before. So we're masking asynchronous exceptions. We're running our before or acquire computation. We're restoring asynchronous exception behavior, interrupting behavior for the computation that the user is asking us to run. We're making sure to pass the resource that we've acquired to that computation so the user can use that resource. On an exception, we're going to run our free or after computation. And if there's no exception, we're going to run our free or after computation. And we're also going to return a result. So we're going to be using bracket a lot because it's very helpful for acquiring and managing resource lifetimes. I'm just going to read this statement here. Yep, so this is just talking about the interruptible behavior. And you can see an example here where they've, again, this kind of with pattern, where they've wrapped this bracket call in with. So it's going to open a file and pass it to the rest of the user's computation. And then make sure to close it at an appropriate time. So it's important to mention as well, in terms of this acquire computation, you should only run one blocking operation during this acquire. So if you need to open multiple files, don't go bracket open file and then like a do statement, open the second file and then open the third file. I'll demonstrate that. Don't do this. Don't open two files in the same acquire thing. Should only have one blocking operation. So if you want to acquire a second file handle, then just have another bracket, just a nested bracket. And then some work here. So the reason for that is that I'm forgetting the reason for that. That is the only way you can be sure that those resources will be acquired and released. And I just had, here we go. I really recommend this book, Parallel and Concurrent Programming. I'm just going to open it up. Give me a sec. Great. And then we're going to go look for one. Here we go. But before, so that talking about the acquire operation, should perform only one blocking operation. An exception raised by a second blocking operation would not result in after being executed. If you need to perform two blocking operations, the right way is to nest calls to bracket. So if you want more information about that, I really recommend this book, Parallel and Concurrent Programming in Haskell by Samuel Bennett. Really useful, fun read, good projects, and we'll be touching on this stuff later. So you might notice that this is kind of ugly. Like nesting these calls to bracket, it might be fine if you're acquiring, say, like one or two resources, but if you're acquiring more, it's like becomes like this nested hell. So there's this monad called the continuation monad, and what the continuation monad lets us do. Let's go have a look. This one. Is it lets us compose these bracket calls in a nice way. So let's look how we might construct one of these. Here we go, probably the conti. Excuse me. All right, so let's grab this constructor. And let's like write a function to open a file. So with file, and let's just give it the file name, bracket, open file, file name, we'll just say it's always going to be in read mode. Afterwards, we'll close the file, and yes, then we'll have a function, some work that we run on the file. Okay. Oh, yeah. Get rid of this. Why do I have bracket here? Ah, let's get rid of that. Excellent. System.io and read mode, and just doing some imports. Let's look, what is the type signature for this thing? So, the file handle. Great. So given a file path, we'll give you a handle. You give us this computation which accepts a handle and runs some computation, and then we'll return the result. So you would use this, like, let's say you had your main program. We were like, oh, do we have a file? Yes, let's open the readme with file readme.md. Just hope that's, yep. And then we've got the file handle for the readme, and let's see, what can we do with a handle? Just see if we can read a line. Yeah, here we go. hgetLine. So hgetLine from the readme. It's going to return to us a string first line, and then we'll print that first line. What have I done here? We'll make sure to import this. Great, let's see if that works. There we go. There's the first line of the readme. So this has made sure to open and close the file. But again, if we start, let's see, what other files do we have? Notes.md. Notes. You know, if we start wanting to open multiple files, you know, this stacking of this nesting gets a little bit inconvenient. So what we can do is let's go with file cont. So if we have with file, and we want to produce, let's just leave this as undefined now. What we want is something that's like file path, and let's get rid of that, to this cont t then the m is io, str, what is this a? We'll come back to that. Sorry, it's been a little while since I used cont. We're not going to use cont in this project. We're going to go use resource t, but I want to motivate that. So let's try and do that. Just going to import library. Oh. da. Come back to that. Okay, great. Okay. Test.row. Oh, what's going on here? Bear with me a sec. Okay, that's working. Where is this? Control monad cont. Cont and conti. Cool. Excellent. So, how are we going to make one of these? I think we can just do this. Oh, come on, Haskell image server, you can do it. Please, error condition. Ugh, great. Okay, so one, oh yes, that's right. There we go. So essentially all we've done is we've wrapped our bracket function in this contt constructor. And now we've gone from this type signature to this one. What this lets us do is we can, instead of doing this, we can go with file cont readme.md, get the readme handle. Then we can go with file cont notes.md, get the notes handle, and we'll just print the first line of person. Lift IO, because we're operating in the cont monad now, we're going to have to lift our IO computations or embed them. And first line of notes H, and first line N. Alright, so the type of this, if we try and run this now, it's going to say, oh, I was expecting an IO function, but this is a contt IO. And that's not quite executable yet. So what we have to do is we have to use this run contt function. So that'll take a cont computation and run it for us. So run const, because we want this to be IO. Oh. Now is that enough? Okay, so we've got our, yes, let's flip run const. So cont refers to continuation. So what's happening here is that it's saying, okay, I'll run your cont continuation computation, and then I want you to pass me the last element in the continuation. So it's like a series of functions that are being called. It's like I want you to give me the last function that's called, and that's what this argument is here. And all I've done is flip this so that I can give this argument first, which is just a little bit more sane. But yes, this lets us more easily compose these kind of bracketed operations. And for a long time, this is what I was using. I was working with, I think nodes.md has an empty first line. Yeah, there we go. So for a long time, I was actually using this because I started with the bracket pattern, and it seemed like a nice way to compose these because you end up doing like 20 of these, so you don't want to nest every one of those calls. Um, However, so something about the bracket pattern is um, if the, if the closing of the resources is abstracted from you, like it is with this with file, it becomes difficult to free resources before like one of these exit conditions. So bracket will free your resource if like the program finishes or there's an exception or an asynchronous exception or whatever, that's when it's going to free the resource. What if you wanted to free a resource before that point and then recreate the resource? And so like essentially replace the resource. You're going to free the old one, create the new one, and then reinstall kind of like that behavior of like, please close this when an exception occurs or whatever. That can get a little bit difficult, especially because these two computations, these two files that we've opened, the order doesn't really matter for the results. So if I switch these around, still going to get the same result, which is the readme first and then the notes.md second. So the order of these operations don't really matter, but we do want to do both. And in that case, there's sort of this implicit dependency here. Like if this one's created before this one, and we throw like an exception here, then readme will get freed first, and then notes will get freed. But what if I just wanted to free notes? It's like there's no way that I can throw an exception that will only free notes and not free readme, which becomes very annoying. Because what we're going to do is we're going to create a swap chain, and the swap chain is going to get recreated every time the window resizes. And so what we want is to be able to free that swap chain without freeing anything else. We've got this kind of interleaving happening. And that's where monad resource comes in, or resource T. So if we go have a look at that, resource T has a similar interface. So let's look for allocate. So we've got the same sort of thing where we're allocating a resource and then freeing a resource. But what it's doing is it's giving us a result that's in this monad resource M. So monad. It's resource monad. And it's not just giving us the resource that we've allocated, it's also giving us a release key. So what we can do with this release key is early release the resource. And what it does is it deregisters, if we were to early release a resource, it deregisters it from the list of cleanouts actions that have to occur if an exception occurs or when the computation finishes. And that's great so that we don't double free. And it's also going to be useful for us because we can release a specific resource, no matter what order we created them in, we can release them on demand in any other order, which is great. And again, it's got like all of the exception safety that the bracket pattern has, but is a little bit more flexible. And that's going to be good for what we need. So the only thing that we're going to add to this is that it's kind of annoying to get this separate result where it's this tupled result where you've got a release key and then the element. Like you'll forget what the release key is for, or the user reading the code will forget what the release key is, or not know what the release key is for. I kind of wanted to just have a little container for this. So instead of returning a release key, we return like a resource, and like you can just call like get on the resource, get the A, and you can call free to release the resource. But the release key is like kind of abstracted. It's a poor word, but uh, hidden from the user. The user can just call free on this resource. That's what I wanted. Um, I won't go over exception safety here for the Mono resource. You're just going to have to trust that it does work, and I'll leave that up to you to investigate. Um, Later, you can use what we've seen here to kind of demonstrate that. Mono resource has exception safety. But what we're going to do is we're going to create our own little resource type. And all it is it's going to have the resource that we allocated, the A, and it's going to have this action that can be used to free the resource. So when we allocate one of these resources, so allocate, it's going to give us a release key and the A. We've got this little function here for constructing the resource from this release key and this A. And all it does is it puts the A in the slot, and for the free operation, it just calls release. And this way, we can expose like a function called free, and that'll just free the resource for us. So we should also add a little operation called, let's call it get for now. It's definitely going to clash with something, but we'll give that a go. Great. Oh, what have I done there? So the nice thing about this is that we can start to compose these resources and kind of group their free operations. So when you create a swap chain, you often also create the swap chain image views with it. So a swap chain will have Vulkan images associated with it, but to use those images, you need to create an image view. And so usually when you acquire the swap chain, you'll get those images, and then you'll make some swap chain image views from those images. And both the swap chain and the image views are resources that we want to acquire and free on an exception, or when we want to free them, when the swap chain needs to be recreated, or when the program ends. And so Monad resource will let us do all of that. Let's show an example. So what we're going to do, let's say we've got this. Let's ignore this for now. Just going to return nothing. So we've got two resources. Going to return nothing. We've got some statements here: acquired resource 1, freed resource 1, acquired resource 2, freed resource 2. And what we expect is that when we run resource t, so just like run cont t, we need to run the resource t, and then we'll give it a computation to run. In this case, it's called test resource. Oops, need to make sure I use the qualified import. Great. So you can see that it acquires this resource first, it acquires this resource second, and then it frees the second resource, and then frees the first resource. And the nice thing about meta resource is that it gives you a release key, so you can resource t dot what is release? So we can change the order in which the resources are released. So previously, you can see, forgive all the warnings, that they're released in reverse acquisition order. So acquired resource 1, acquired resource 2, freed resource 2, freed resource 1. Instead, what we're going to do is we're going to like force the release of that first resource first. So you can see that happen here. We acquired resource 1, acquired resource 2, and then we freed resource 1, freed resource 2. So just reiterating behavior of meta resource. But let's say we want to like group these two things so that like we're going to pass the resource back to the user, and the user might decide, okay, I just want to free that thing. And it's, let's say that thing is like some data structure. But what if that data structure is made up of multiple of these monad resource allocate calls? Um, we need to give them some way of freeing both. So what we could do is we could pass back to them the release keys. So we're going to give them 2 release keys and 2 resources. And the resources here are actually just units. So make sure to import. So release key 1, release key 2, resource 1, resource 2. This is kind of annoying because they have to call release on both of these keys. It doesn't make for very nice or fun code. What we could do, though, is we could pass back to them an operation they can run to free the things. And instead of passing the release keys back, what if we were just like, we'll just release it for you. Resource dot free. So we're going to release key 1 and then stop free, release key 2. Have I done the right thing there? Ah. Release. That's the name of the operation. Then the user just has to call this first element. And that's essentially what we're going to do here. What we're trying to do. One of the things we're aiming for here is like, we're going to give the user back this resource from the raw kind of resource T allocate call. And we want to be able to compose these resources together. Like take my swap chain and my image views and slap them together. And if you free that slap together resource, you're going to free both components of that resource. And that's why we have this kind of applicative instance here and this monad instance. The monad instance is perhaps a little bit clearer. So maybe this one actually. So given kind of these 2 resources, we're going to slap them together. We're going to free the first resource first and then free the second resource second. And I'll demonstrate how this is used. So we're going to call from resource T on our allocate call. That's going to give us these resources back. Then let's say we have a data structure, and the data structure is made up of the 2 resources. Now remember, the resources in this case, they don't actually they're just print statements, so there's no actual return result. So we'll just make that unit. Then rather than returning this whole structure, we can just return resource my data. And all we have to do is this. So we're going to fmap the myData function constructor over this first resource, and that's going to kind of partially apply this myData function to our first resource. And then we're going to use the applicative operator to apply the myData function to the second resource. So bam, we've been able to combine these 2 resources. The user can just call free on test resource and it will free both of them. So that's great. And we might even, let's make this a little bit simpler. Let's create our own allocate. And we'll just mimic this. So IO A2, IO this. So this is our acquire the resource, free the resource. And instead of returning to them a M release key A, we're going to return to them an M resource A. Make sure this isn't a monad resource. Now all of that, we're just going to resource t.allocate, and then with the result, we're going to fmap from resource t. I think. What have I done wrong? Oh, acquire, destroy, acquire, destroy. I'm just going to pass the arguments onto resource t allocate and change the result type. Is really all we're going to do, and that's just a convenience thing. So allocate, great, and we head back to our example. Rather than using resource t allocate, we'll just use our resource allocate. We can get rid of this stuff, and good to go. Put these on. These a little bit prettier. Done. So we're relying on the monad resource to provide us with this exception safety. So, like no matter what we do, no matter how much we stuff up these like applicative and monad instances, the resource will be freed. So that's great. It's good for us. We don't have to worry too much about it. And we get this nice kind of, we can compose these allocate operations into like one big one that the user can just like free if they want to. So that's great. So now that I've like gone over, let's just make sure this compiles. Resource. Yep. Just gonna reload the library. We'll load our module. Yep. That's working. So let's just give an example. So say you've got this big program and you're going to acquire a little like test resource. Now you've got your data. It's like a my data. Type of this is resource my data. And then let's say you wanted to print the data. Just print get my data resource.get. So we're going to get the resource out and print it. And that's all we're going to do. Just make sure to add scope type signatures. Should I qualify this import? Oh, and we've got to embed the IO computation because we're printing to the screen. There's no instance of show. Let's derive that. And what else we got? Ambiguous. So let's say this is our main function. We're just going to acquire a resource and print what we acquired, which won't be very interesting in this case. Yep, got it. We acquired resource 1 and resource 2. We print the resource, we free. And we can early free in here. So we could resource dot free my data. We'll just have to lift that. And it's going to look exactly the same. We could also like free and then acquire another resource, my data 2. So we've freed the resources of the first one. We're going to acquire another one, and let's just print that. This is going to be like the kind of typical use case. You can see we acquired resource 1, acquired resource 2. They're grouped together. We printed the data, we freed those, then we acquired next set, printed that, freed those. So this is going to be perfect for our swap chain. So let's get off the examples and jump over to our swap chain then. Actually, I'm just going to take a quick break. It's been an hour and I don't want to destroy my voice. So I'm going to take a 8-minute break and I'll be right back. Um, there we go. Calci, be back. We'll start a little countdown. Cool. All right, I'll be right back. Test, test. All right, we're back. So I thought it might be cool just to mention some of the, just to feature an album every week and also a TV show. Just to some of the things that I enjoy. So, um, album that I've been listening to this week is I Came Home Late from Amalu. Really like it, really recommend it. I'm not at all affiliated with these people, not sponsored or anything. This is just stuff that I enjoy. I recommend. And I've been watching this TV series called Through the Darkness. It's a K-drama, Korean drama. Really recommend that too. Um, so yeah, getting back to our project, we're looking at Swapchain and how we're going to acquire it. So let's start off by filling a structure with, let's look at the type signature. So given the VK context and like a frame buffer size, let's comment that. And an old swap chain, so, or potentially an old swap chain, so you got this maybe option type. Um, we're going to create a new swap chain. So the reason that we pass in the old swap chain is that Vulkan will be able to reuse some of the resources from the old swap chain potentially. So we just pass it in as like an optimization measure. So we talked a little bit about the frame queue before, and it's the same as last time. We're just going to modify it a little bit. Uh, there's no need to recreate the frame synchronization primitives if we recreate the swap chain. So all we're going to do is we're going to look at this old swap chain, and if it's nothing, we're going to do what we did before, which is create the frame queue and return it. But if there's an old swap chain, we'll just return those and reuse those. So that's pretty simple. Um, we've got this swap chain create info function. It's going to fill out a data structure. We're going to see this a lot in Vulkan of like we fill out a data structure with create information and then we create the thing. So we've got a little help function. It's going to take some information, the physical device, the surface, the frame buffer size, and then a queue family. In this case, we're just taking the head. We're probably going to come back to queues and revisit them and make them a little bit nicer. But for now, this is what we're doing. And also, we're going to look at the old swap chain. And if there's no old swap chain there, we're just going to pass in a null handle. And if there is, we're going to pass in the handle to the swap chain. So this is the swap chain recreation or reusing resources that we talked about. So let's just load up the project so that we can get some feedback uh, on what's happening here. We'll start up Haskell language server. We can get the same thing. Yeah. Frames implied. Where's that going to come from? Let's just make an argument. Excellent. All right, so we've got a help function to find the depth format. And so the image format and color space. Okay, now we're going to start acquiring our resources. So the swap chain resource. Let's use our new function, which we're going to have to import. Import qualified. Yep. So it's going to be vk create. So anything with a this vk prefix is just like a raw Vulkan call. Nothing special. Okay, device, context, pass in the Swapchain creation info, and we're not going to use a particular allocator for that. And then when we want to free that Swapchain, go vk destroy Swapchain khr, vk device, and then the Swapchain. Excellent. Call this we'll just call it SC, it's fine. And then we're going to create image views. So what we're going to do here is first up we'll grab the images. So we'll get the Swapchain images. Great. This will have to be and then we're going to for m the images, we'll create a Swapchain image view with the color format of the Swapchain. And then after that, we'll destroy, get these image views in, and we'll destroy them. Great. Get rid of this old code. Cool, so we've got two resources, but we need this whole data structure. So let's do that. So the first argument is going to be the Swapchain. The second argument is going to be these image views. So we're going to be in the resource mode out here. So that's why we're using these composing primitives that we defined before, the functor and the applicative. Now the surface format, well, that's not a resource, that's just something that we've queried previously. So we can just use the applicative pure to lift a a computation that doesn't need to be allocated and freed. We can lift that into a resource. Can do the same with a depth. Same with the extent. Now, forget where we get the extent from, but we'll come back to that. And then the same with the Swapchain frames. So, what do we called it? Frames Q. Great. Now, we should have gone ahead and made the Swapchain. I believe. Oh, where did we go? Okay. Image format. Let's go Swapchain, create info. The image format is this format. What's wrong with that? Oh, we're looking for a surface format. So, where do we get the surface format from? We might have to query that. It's made up of format and the color space, which we got before. Great. And the last thing left here is the extent, which is just pure VK, that's VK Swapchain image extent. Great. So hopefully that compiles. Looks good. So there we go. We're able to acquire Swapchain, reuse any resources that can be reused between Swapchain creation and destruction, which again is happening every time the window is resized. Yeah. So I think that covers the Swapchain. We'll almost definitely revisit this, but again, this is as we're building this, we're not aiming for perfection. We're just iterating. So we're going to get to a point where we can render a triangle to the screen. Then we'll work on making these kind of things more robust. And I'll probably work on some of that stuff off stream. And you guys can follow that on the commit history of the project. Because sometimes that's not very entertaining. So just to, because I haven't mentioned this stream, you can find the project at github.com/sambnt/RRT. And you can follow along with the commits. And we'll be committing live on stream. Cool. So let's commit my resource Swapchain. What changes have we made there? Nothing important. We'll come back to that. Apologies. Oh, hey, to use at work. Trying to learn Haskell. How are you finding it? So we'll definitely be covering bits and pieces of using Haskell here. Um, uh, but it's not entirely like a tutorial series. But on my YouTube channel, which you can find with that same handle as Twitch, Sam Bennett _TV. Hopefully, I'll start uploading videos on specific concepts, so that it's there's a little like a bit of a better on ramp into this project, and those specific concepts will be a little bit more helpful. But yeah, this is definitely still learn stuff watching this. All right. Let me just open my notes. We'll figure out what to do next. So if we head back to our example, what was it called? What do we call it? Examples triangle. Good name. We have created a window. We've initialized a Vulkan context. Excuse me, I'm just gonna close the window. We've read in our simple shaders. We've created this kind of like renderer thing, and we don't really know what that's going to do yet. Can we see visually what this program does? Hopefully today. So far, this is the second stream. So far, it does nothing. It does open a window, I'm pretty sure. So we'll try and give that a go. Load raw.examples.triangle, and it's going to print hello world, and we'll give it a little thread delay so the window stays open for a minute. Uh, so here we go. We've got a window on the right here. Um, there's nothing on it, so it's just showing my background. Uh, and that'll close in a second. But the idea behind this project is I was inspired by frame breakdown a long time ago. I was inspired by this. It's a frame breakdown of Doom 2016. And what it does is it shows you how, you know, Doom renders itself. Um, so you can see that there's like a depth map. Uh, there's this like velocity map for tracking the velocity of pixels. There are all of these textures that are like composed together to make this like really cool, beautiful game. Um, and I really enjoyed this breakdown. And I was like studying computer graphics at the time, and I was like, oh, I want to try and do this, but like at that time, like really only knew how to use OpenGL, and the whole idea of like multiple render passes was like way outside of my comfort zone. So many years later, I wanted to write a Haskell program that will let me experiment with frame breakdowns and sort of create my own and experiment with like easily creating new render passes and new textures to render to, and then composing them together to make a final image. So the goal behind this rendering engine is uh, to experiment with making pretty pictures, basically. Um, yeah, you can find all kinds of breakdowns. This one's on Doom, but there's a great one on Slime Rancher. Um, this one? No. Oh no, can't find it. Oh, maybe. Ah, anyway, there's a really good frame breakdown on Slime Rancher. And yeah, so the idea is that we're going to create like a bit of a high level interface where we can say like, oh, I want to go in here and be like, I want a color attachment to render my textures to, and then a depth attachment to render my depth information to, and then maybe like a position attachment. Um, yeah, or this would essentially be a color attachment with a different format. Um, so we want to make describing render passes and the textures they render to, and then the way they're combined together easily, and sort of abstract all of the like Vulkan work and resource management that has to happen underneath the surface. Um, so unfortunately, we're not at rendering a triangle yet. Do you have a particular interest in learning Haskell? Like anything that you're working towards? All right, so I think the next thing we want to look at is the renderer. So we're going to have to make a swap chain for this renderer. And we're going to make it a resource because we know that when the window is resized, we're going to remake the swap chain. Can Haskell be used to make a trading bot? A very precise one. Uh, there are people doing that. Haskell, Japan, trading firm. I think it's these guys. Um, well, it looks like they're using Rust now. Maybe that's maybe a little bit outdated. Uh, Here we go. Trading firms using Haskell. Barclays. What is going on here? So I think so. Um, I have heard of people doing that. I haven't looked into it myself, so I cannot confirm. Um, yeah. So the only real limit, like Haskell's compiled down to like C++. So, well, it's compiled down to assembly. So it's a compiled language. So it can be low latency and fast. The only thing you have to worry about is garbage collection. Um, and for embedded systems, you like what runs alongside your program is a runtime environment, and that does things like look after memory and resources and stuff. Um, so sometimes you have to worry about that, but we're building a computer program to render things, and that's definitely going to be able to render things at low latency. So it's definitely possible. Um, and I think with trading bot, you're not worried about resource constraints, probably not executing on embedded systems. I don't actually know, but you're probably not. So there's no real problem with doing low latency things in Haskell. I wonder if there's any resources on that. Low latency garbage collection. Yeah, I'm not sure. I'm not sure. That doesn't look entirely relevant. But yeah, I don't see a reason why not. What are you hoping to trade? So we're just going to create a swap chain. So let me just refer to my notes actually. Render frames and the frames swap chain. We actually might want to access this swap chain from different threads. So I'm going to put it in a T-bar, thread safe variable. Cool. So with swap chain, what do we need? Give it the context. I'm going to give it the number of frames in flight. We'll make that configurable argument. But yeah, thanks for joining the stream, Tees at Work. Feel free to ask any questions related to this or not. Great. Frame buffer size. We're gonna need to figure out how to get that. And because this is the initial swap chain, we are going to put nothing in for this old swap chain because we do not have an old swap chain. Great. So we'll create new T-var with our initial swap chain and just call it. And we'll return that. Make sure to import what we need. And import with swap chain. Did I not expose that? Swapchain. Okay, great. Now let's see what our problems are. All right, so one of the problems we have is that we don't have the current frame buffer size, which we'll need to get from GLFW. So in our context, let's have a look at how we did this in our test project. Separate context, and I see. Great. Okay. Well, so what's happening is that in our context, which is sort of just like a bunch of Vulkan data that we're going to use, um, we are going to add a method of getting the frame buffer size. So let's call it get frame buffer size. And, you know, we might come back to this later and be like, this is stupid. Why are we doing this here? But this will work for now. And we'll make refactoring a weekly part of this project. So get frame buffer size. When we're creating the VK context, we've got the window, which means that we can get the frame buffer size. So get frame buffer size equals something. And if we go to our window, we actually have a function there already for getting the frame buffer size. Let's give it different names so that we're not aliasing. And make sure to import what we need to import. Window. Window. Get frame buffer size. Great. That'll fix itself soon. So now what we can do when we're creating the render is from the VK context we can get frame buffer size. It's an IO computation, so we're going to have to embed it from the context. Let's make sure that's exposed. Get frame buffer size. Can context. Great. Put that in here. And let's see. What are we missing? Ah, that's right. So in our triangle example, when we're initializing the renderer, we need to put in the number of frames in flat. So this is like the number of frames that we're going to, like with the swap chain, you've got multiple images, you know, like render to one and present another. So this is kind of the number of frames that we're gonna, like if you were triple buffering, like vsync triple buffering, you have like 3 frames in flat. Yeah. So we're just gonna start with 2. Doesn't really matter for our purposes, or at least not right now. It will later. So let's just run this and see what happens. Cool. So we got to get rid of this thread delay. So nothing's happening, but also getting no warnings either. So we've enabled validation layers, which means that if we do anything stupid, it'll tell us, which is great. All right, got Swapchain. Let's go. I'm going to refer to my research project and examples. triangle. So what I did before I started this stream was just did a little bit of like research and development on like how we make this. Like I didn't want to come in here totally blind and just be fumbling around. Um, and it was great because I made lots of mistakes and learned lots. Um, but I made a little example where I rendered a triangle basically using like raw Vulkan calls, and it's really like horrible to read, but it is helpful here. This will help me get my bearings, understand like, okay, what is it that we need to tackle next? Just open up our notes too. So we've created the Vulkan instance, we've done surface, done all this, well, some of this. All right, let's start with the frame. So if we go back to our triangle example, we've got this kind of idea of submitting a frame, submitting a draw call to a frame. So let's write this with frame function. Render with frame. What we're going to do here is we're going to acquire the next Swapchain image so that we have an image to render to. Mm-hmm. Oh, excuse me. Oh, that's right. Excuse me. Quite a lot going on there. All right, so this could be called from multiple threads. So, okay, we have to pass the render in first, and we're going to acquire the swap chain. Well, we're just going to read the swap chain variable. Let's make this, oh, we'll just leave it as for now. Swap chain from the renderer. Great. So now that we've read the swap chain, we need to get the next frame in flight. So how do we do that? Oh, that's right. So we have these synchronization primitives that we've created a queue of, and that's so that multiple threads can get these synchronization primitives at the same time. We've only given enough for the frames in flight, so having more threads than frames is not going to help. The other frames are just going to be blocked. We'll probably have to do like a deep dive on multi-threaded stuff later. So we'll just pretend this is not multi-threaded for now. So we've got swapchain, we've read the variable, and a pure undefined, just so we're not getting errors. Unhelpful. Import this. Okay, so let's create a function to get. So given a swapchain, give us the frame synchronization primitives for a period of time. So we covered this at the start. This is just this pattern, this bracket pattern, where we're going to acquire a resource. So in this case, we're going to read an element from the queue. Swap chain frames from the swap chain. And then at the end, or if there's an exception, or if our thread is killed, we are going to make sure to return that frame, those frame synchronization primitives to the swap chain. And we've just got to import this stuff. We'll make these qualified because we've already imported STM. And bracket needs to come in. And what have we done wrong here? Oh, that's right. And we'll just keep this monad generic, although it's almost certainly just going to be IO or a monad resource. Cool. So yes, so the width pattern, the bracket pattern, all it is we're acquiring some scarce resource, we're returning it, and then this is the computation to do after acquiring it and before returning it. So in this case, this is the last argument here, this, but we don't have to specify that. Cool, so got the swap chain with next frame in flight. Swap chain. Now we've got these frame sync primitives. We can do something else with them. Make sure to import that. What's wrong here? Ah, yes. Resource.get, because we have a resource. Make sure to import that. Import qualified root.util.resource. Cool. All right. Now we're going to wait for those fences for going to wait for the frame in flight fence to return. So we're going to make sure that we actually have the frame. We're going to acquire the next image. So as part of the frame sync primitives, oh, done something. But, oh, looks like it's still working. Never mind. Sorry. Push something over in my OBS. All right. So what we're going to do is we're going to acquire the next image. So given the device, okay, we're going to have to pass in the VK context here to this structure. Just put that in here. So, yes, given the divide. This is a raw Vulkan call, so anything with VK is a raw Vulkan call. We get the VK swap chain out of swap chain. We're going to wait a potentially infinite amount of time for the next image to become available. And we're going to acquire that image. So we've got an image index. And so what acquire next image can do is it can say to us, oh, like your swap chain has resized and now your swap chain is out of date. Like the window's resized and your swap chain is out of date. So we have a little function here called throw swap chain out of date. We have two of them. Throw swap chain suboptimal. We're going to add those here. Make sure to import what we need. So the problem with this is that it returns the result as like, I don't know, just this weird type where it's like, okay, there was an exception and it's out of date, but it wasn't like a Haskell exception, so it's not going to behave like a Haskell exception, it's just a result. So we're just going to make our own swap chain out of date exception type and throw that. This is just a little implementation detail. It's not important. Basically, what we're figuring out is a swap chain out of date or is it suboptimal? And in both cases, we're just going to throw the same exception, which is that the swap chain is out of date. And it's that this will be our trigger to recreate the swap chain, which is where we'll get into the whole recreating the swap chain thing. All right. So what this does is just wraps this computation, make sure this is going to throw the exception. So acquire, get back to where we were. Need to oh, here we go. Make sure we import everything. Lots of fun. Great. So, I'm going to acquire the image. I'm going to do some stuff. At the end, we're going to present. So, the user's going to call with frame, and we're going to do things like acquire the frame and make sure it's ready and all that kind of stuff. Then we'll call their code to do all the work, and then we'll present that work. Again, more imports. And when we're presenting the image, that's when we'll get this swap chain suboptimal message. It's not the right type. Functor void. And we'll need to deal with the %q later. Looks like I'm aliasing that. It's not so good. Alrighty. Let's just take a look at what's compiling, what's not. Okay, yeah, there's issues here. Da -da -da. Sometimes I wish I could just import everything. Just figure out what I need to import. Surely you can do that. Yep, that's fine. Yep, no worries. Cool. What do we use the image index for? Okay, so we use the image index down here. This is what we're going to present to. In here, we're going to like take a bunch of commands. So the user's going to submit a bunch of commands. Like draw this, draw that. We're just going to record that to a command buffer. We're going to submit the command buffer. Then we're going to present. But for now, we're just going to leave this up to the user. So yes, I'm going to have to deal with queues. So a second. All right, queues. So we found a bunch of queue families, which is great. But these aren't actually queues. They're just the indices for the queue families. So we've got to acquire and create the queues. I think a good place to do that is in this context here. So again, we're going to add some elements to this structure, and so they're going to be the presentation queue. These are queues you can submit commands on, and on some hardware, these queues are all going to be the same queue. You now have a queue for presentation, a queue for graphics, a queue for transfer, and they're all going to be the same queue because that hardware doesn't support multiple queues. Or on like most dedicated graphics cards, you're going to have a separate queue for graphics operations, which are like draw calls, presentation operations, which is like present this image, and transfer queue operations. So that's like uploading data to the GPU. So you can be like submitting a command to upload data to the GPU at the same time that you're drawing or presenting. So that's great. And we're just going to create these queues when we create the context, or acquire them when we create the context, and make them available to the rest of the program. Now you can use more complicated things where you have multiple transfer queues, like my graphics card has multiple transfer queues, but we're just going to keep it simple. Just go one queue, which is like a lot of rendering engines do that anyway, so it's not a problem. We're unlikely to be bottlenecked there. So this means that we are missing a few things here. And a transfer queue. All right. Actually got some queues here. So what we can do is after we create the logical device, we can create the queues. Logical device. What's that called? Graphics queue families. There we go, there's a graphics queue made. Present queue families. Presentation. We got transfer queue. So these queues are actually made in this structure here, in this call here with logical device. Go have a look. So you have to create a bunch of device queue create info structures. So when you create the device, you pass in the queues you want to create, and it creates them for you. And here we're just retrieving them. So yeah, we are just retrieving them. So we'll go have a look at this operation. Get device queue. So given this queue family index, get a queue within the queue family index and return it. So we're not actually creating anything here. Maybe we are, we're not sure, but it looks more like we're just acquiring something that already exists. So transfer queue. All right, let's put them in. I wonder if these are thread safe. Doesn't look like it. Host access to the queue must be externally synchronized. What that means is that multiple threads can't submit to the same queue at the same time. So we're going to have to be careful about that. That's okay. What I imagine will happen is that we'll actually I've already done some research on this. So what happens is we'll create a queue, but what the multiple threads will record their draw commands to command buffers, and then a single thread, like our main thread, will group all of those command buffers into a larger command buffer, and then it'll do the submit. So we don't have multi-threaded submit, like we don't multi-threaded queue submit. We only multi-threaded draw record, if that makes sense. So the way that we synchronize access to the queue is just we have one thread that submits to the queue. But in order to get efficiency, we'll have multiple threads submitting draw command buffers, draw calls. Right. So now the presentation queue is part of the VK context. So we can just grab that out. VK context of the renderer. Yep. And then VK presentation queue. I have to import that. And yeah, that's good. A quick look at what our errors are now. Cool, so we're compiling. That's good. Let's let's have the user return to us a list of drawers. So there are a few things we could do here, and we're probably going to iterate on them. Um, when I first tried this, what I did was like I got the user to like allocate, like I could allocated a command pool for the user. I gave a command pool to the user, and I like let them, just allocate buffers from that, and then submit whatever they wanted. For this, I think we're going for a little bit of a simpler approach, and we're going to hopefully iterate on that. Where if we go to our triangle example, we can see with frame, we've got this submit uh, submit function. I think what we'll do instead is we'll do something like this. So we'll just get the user to return a list of drawers that they want to do. And we might sort those drawers by shader. That would be a smart thing to do. We can do some things. Wonder if we can even make these thread safe so they have multiple threads submitting drawer calls. And then we'll kind of group them up into a structure or a list, and then we'll iterate through that list, and we'll allocate the command pool, allocate the command buffers, record the drawers, that sort of thing. So like it's a bit of a higher level interface rather than the user having to like record the command buffer and then record like all of the individual things. So for example, this is what the draw code would kind of look like. It's like they allocate a command buffer, uh, they're doing all the waiting and stuff. They begin their command buffer. This is what it would look like. They have to require a frame buffer that matches the render pass they're about to do. Specify the clear values and then begin the render pass, submit the begin render pass, set up the viewport and scissors, uh, bind the right pipeline, submit the draw call, end the render pass, blah, blah, blah. So what we're going to do here instead is like, if they want to, like, we'll do this for them. Like, we'll create the render pass, we'll create the pipeline, um, we'll make sure to set the right render pass and pipeline for the particular draw call, and then we'll run their draw call. Um, and that way they should have like, there's still going to be a lot of flexibility. We'll make it even more flexible as we go, but we can look after things like allocating command buffers and the like. Cool. So it's been another hour. I'm just going to take a little 8-minute break and then come back. So thanks for listening, guys. I know it's not super entertaining at the moment, but soonish we should be out of triangle. So thanks for your patience. All right, be right back. Right, we're back. Hey everyone. So yes, we're working on our Vulkan Haskell rendering engine. So we have, once we fill out this structure, we have enough information to render our simple triangle from these descriptions and then this draw call. But, so we check out our renderer. What actually happened when we made that pipeline and made that shader is we just stuck what the user asked us to create into a variable and then returned a handle to it. Look at the type of this handle. It's just an integer. And we're going to derive some stock types on it. Just for later. Um, but handing back that handle, we didn't actually create a pipeline or a shader. We kind of lied to the user. So what we want to do is create that pipeline and that shader and create all the Vulkan resources necessary so that we can use them. After we get the drawers, we can let's sort the drawers by something by shader, and then we will sort the drawers by shader, and then we will um, let's have a look. We're gonna have to begin a render pass. We're gonna have to set the viewport. Excuse me. Wow, I'm burping like crazy today. Set the scissor. Bind the pipeline. And then we can actually do our draws. And this is going to be like for each render pass. And going to do all this stuff. At least like a simple overview. So, what does that actually look like to do? So in the pipeline info, we got this vertex input we can ignore because we're not going to use it. This compare up. We've got this render pass layout. This render pass layout, it's got a few attachments, subpass description, subpass dependency, and yeah, I think one of the first things that we should do is create the attachments necessary for the render pass. So what's necessary for the triangle? Let's go back to the triangle example and actually fill this out. So previously we just had empty lists. We actually just need a single, oh, we don't need that. We need a single attachment. And what options do we have? What's that called? Render types? Great. Cool. So, well, we actually need a Swapchain attachment because we're going to render directly to the same frame which is going to be presented to the screen. So we've got that Swapchain attachment here. And then we need to fill in the attachment description. So some information about that. It's just a very inconsistent indentation style, but whatever. Hang on a sec. I think I've done something wrong here. We'll plow on ahead. All right. So the format is we'll just say the Swapchain color format. So we don't actually know the format. It's kind of I mean, as the end user, um, the format might change depending on the device or whatever. So um, we're going to defer commitment and just say like, oh, give me the Swapchain color format. The samples, we're just going to say one bit. Not doing anything fancy here. Um, and we'll simplify this as we go, but for now we're just exposing everything. So this is the load up. So what to do when you load this attachment? In this case, we're going to clear the screen. Store up, we're going to store it. Now for the stencil, so this is the store up. Now there's the stencil load up and the stencil store up. We're just going to say we do not care. We're not using stencils right now. Store up, don't care. So leave it up to the driver. Now the initial layout is undefined. These are all Vulkan concepts. But at the end, this is going to be what we present to the screen. So we just need to say that we want the final format to be, like presentable. Cool. And for the subpasses, we have to submit a subpass description. It's a graphics subpass, bind point graphics. We're not going to have any input attachments. So this would be things like textures that you're using or attachments that you're using to influence like the next attachment. Like you might in deferred rendering you might output a buffer that's like got all the position values of every fragment, and that might be an input to a lighting render pass, subpass rather. In this case, we only have one subpass, so we're not going to have any input attachments. We've got a single color attachment. That's the first element of this list, so we're going to give it the index of 0. You have to refer to it using this structure. And then it's going to be a color. Yep, so it's a color attachment. Got no resolve attachments. This is for like multi-sampling, I think. No depth stencil attachment because we're not doing a depth test at the moment. And no preserve attachments. Now I have used this preserve attachments before, but I forget what for. Cool. So there's our subpass description. Now subpass dependencies, we only have one subpass. So this is relatively simple. It is subpass dependency. So from this is the source subpass, and the destination subpass is us, or subpass 0, the first subpass. I'm just going to copy this from over here. Really, this is just like this is just not even really sure why this is necessary, but this thing's like, don't do. Oh, I'm not even going to try and explain it, I think. It's sort of like, given the last stage of the source, like this could be like read, and this could be write, and this could be read. So this is saying don't read from the color attachment output bit until the color attachment output bit has been written to by the previous subpass. So I'll say again, don't read from the color attachment output bit until the last subpass has written to the color attachment output bit. But in this case, we're saying don't write to the color attachment output bit until everything has done on the color attachment output bit from the previous subpass. Until the previous subpass is finished with the color attachment output bit. And the subpass is just like external, which is like the first one. So I guess it's just saying like, don't render until the last thing's finished. Until like last frame or whatever is finished. I'm not 100% sure, but that's how I'm thinking about it. All right, so we filled those out, and we are 100% gonna like not make the user fill these out in future, but right now things are bad, so we're just gonna do that. Okay, now we actually need to like, for example, this attachment, we actually need to create it. So let's over to the renderer and go ahead and creating it. So when we first create the renderer, there are no pipeline or shaders, and then like the user's gonna create some. So like at some point between creation and us starting the frame, we're gonna need to like create the attachments. Um, um, I think the best time to create the attachments is probably when the user declares them. We might have to revisit this, but um, we don't really want to be creating the attachments every frame. But how about we just do that because it's easier? Let's start with that. So what we're going to do is, we've got all this stuff about getting the next frame. But first, every frame, we're going to create the attachments. Let's start with the attachments. So let's read, and we'll move this to a better place later. But for now, let's just do it here. Let's read through, let's read the TVAR of pipelines. Because remember that the attachments are found in the render pass layout of the pipeline info. And the structure of these, the shader and the render pipeline info is totally arbitrary. It doesn't match the Vulkan underlying structure, but I think that's good. And we might come and revisit this later. But for now, this render pass layout is found out in this pipeline structure. So let's read the pipeline infos. To lift IO. Cool. So, and then let's get the attachments out of it. So let attachment infos equal pipeline infos. And then we're going to steal the pipeline render pass layout. So for each pipeline info, we get the pipeline render pass layout, and then once we get the pipeline render pass layout, we're going to get the render pass attachments. We just got a little like extraction function here. From all the pipelines, we're going to get a list of attachments. Someone actually knows Haskell and uses it instead of saying they know Haskell when they don't. Awesome. Yeah, thanks. I appreciate that. I've used Haskell at work for for 6 years almost. Yeah, for 6 years. Um, uh, yeah, yeah. What am I trying to say here? I do see a number of like clickbaity videos that are like, I tried learning Haskell, I tried using Haskell until I couldn't anymore, and it's like a 30-minute video about the kind of day they spent with Haskell. I really like Haskell for like the interesting ideas that it has. Um, but it's also just very practical. Like I've used it professionally for 6 years, and a lot of the stuff that I wrote was really just dumb and simple. So um, there are definitely like it's definitely a hurdle of stuff to get over to start, um, but a very practical language. So would recommend. Uh, would definitely say it's not easy to learn though. It's not necessarily super fun. It's good to do it in a low pressure environment. But anyway, I appreciate that. Thanks. Oh no, why can't Elixir people get a job? Oh no. Oh no. You know, I was actually talking to a friend the other day and they were trying to get into software development and so they did boot camp in Elixir and then they had trouble finding jobs. So that's not the first time I've heard that this week. Um, why do you think no one uses Elixir? I really don't know anything about Elixir. All right, so we've got the attachments for each attachment. We should be able to create an image. And later on, we're going to like use a proper allocator to allocate a big block of memory and um, sub-allocate from that. But right now, we are just going to we're just going to use the default allocation scheme. So what are we looking for? Attachments, attachments. So I'm just on the side here referring to some just a kind of a raw Vulkan example I did a little while ago. Go. Oh, well, actually, for anything that's a Swapchain attachment, we don't need to uh, we don't need to create an image because that image has already been created for us. Yeah, no one uses Elixir because everyone isn't cool. Yeah, oh, I know that feeling. It's a Vulkan renderer, yeah. Okay, writing a native C function for Elixir that uses Vulkan. That's tough. Yeah, I mean, I I mentioned before, but like I was really inspired by these like frame breakdowns, um, where they kind of talk about, this is how a frame is rendered and like these are all the textures and how they are combined. Um, really inspired by that, and I was learning OpenGL at the time. And I was like, oh, cool, I'll just do this OpenGL, and like I found it really, really difficult. And so like it's been like 8 years since then. I just learned Vulkan for fun from the Vulkan tutorial. And there's a decent Vulkan library for Haskell that's really just a mirror of the C API. Um, And then it seems like the concepts that are presented here in these frame breakdowns are a lot more easily translatable into Vulkan. Um, just like the idea of render passes and things like that. Uh, so that's kind of the goal. The goal is just to make a nice high-level interface for describing these frame breakdowns so that I can like I really like how Doom looks. It's like if someone can explain that how it works like this, surely I should be able to implement it. And so I guess this is a step on towards that. Um, yeah. Yes, Vulkan is not user-friendly, and yeah, being simple is a good start. Yeah. So, all right, so we figured out that we actually don't need to create any images for Swapchain attachments. So let's just we'll put that in here. Case attachment info. Of Swapchain attachment, which is the only thing we have at the moment. The only option we have. We're going to do nothing. So we'll just mm, shall we get our imports lined up? Okay. No. Ah. Okay, just a little bit of type messing around there. Cool. Just return nothing. All right, we'll have to come back to that later when we actually have something to create there. So if we don't need to create an image, what do we need to create? Well, we're definitely going to need to create a render pass. So let's start there. Um, so remember, this is happening every frame. So this is not ideal, but that's okay. I'm keen to see it. This is only my second time streaming on Twitch, so I don't know if you can post images, but yeah, if you want to show it off, post an image. I'd be happy to have a look. Um, Endeavor OS, that sounds interesting. Oh, I do not have a Discord. Just started this week, so oh, I like purple, so this is already looking good. Okay, Archbase. Oh yeah, I love purple. Yeah, cool. I'll have to do some more research. Yeah, so just FYI, I've got a YouTube channel. It's like SamBNT underscore TV. SamBNT underscore TV, and I'll be uploading these streams in full there. So I've got the first one here if you're interested, and you can follow along with the project at here, github.com Sam Bennett, SAMBNT slash RORT, RORT. Um, and yeah, you can follow commits live and everything. But let's get back to it. Okay, we need a render pass. Render pass create info. It's like a lot of things in Vulkan. We got to create a structure before we can create the thing. We're going to fill this with information. So, attachment descriptions. So for each pipeline. Figuring this out as we go along. So each pipeline info has one render pass layout. So for each of those, we're going to get the render pass layout out. With the render pass layout, we've got a set of attachment descriptions. So let's create a little function here to convert these attachment descriptions to Vulkan attachment descriptions. Attachment info to VK attachment description. And what we're going to do is VK attachment description. VK0. And then the format. So if we've got a Swapchain attachment, so case attachment format in the description of Swapchain color format. Look, I haven't done much. I've been streaming for like 2 and a bit hours, so I've kind of gone past my plan. So I'm kind of like stumbling in the dark a little bit. But what I'm trying to do is I've managed to create a swap chain. We're able to get the next frame, and we've got draw calls from the user. But what we need to do is like create the render pass and then set the viewport and bind the pipelines. And to bind the pipelines, we need to create the pipeline. So we really need to create a bunch of resources, Vulkan resources, based on the things that the users asked us to create. And in this case, I'm going to start with the render pass. So what I'm doing at the moment is trying to convert my attachment description into a Vulkan attachment description that I can append to the render pass. So if we have a Swapchain color format, we're going to need more information here. We don't know what the Swapchain color format is at the moment, so we're going to need to pass that in. So how does that work here? Swapchain format, surface format. Yep. So let's get the Swapchain color format passed in. Oh, sweet. Oh, let me open up that video. What's it like using Arch? It looks pretty. Have a look. Okay, so we're just having a look at a um Endeavor OS, at Endeavor OS. See if I can make this quality a bit better. Submitted by chat. Cool. I really like the pink. I got Steam installed. Nice. Sorry, I can't play audio right now. But check out the video if you want to watch, if you want to listen to the audio as well. Oh, I like this cat thing. Like these fun things, like they're important, I think. Um, it makes things fun. Like I don't know, it's nice. Cool. How you wish you could kill your pets? Great. Oh, I like this code editor too. I really like this kind of old style Windows, like frames. They're nice. Yeah, awesome. It's like low quality pixelated background. Great. I'll watch the video of the audio later. That's cool. I like that. I really have put zero effort into writing my desktop. And it shows. Shows. All right. Cool. So I've gotta head off in like 15 minutes. So let's try and get something. So yeah, we'll just use the Swapchain color format passed in because we don't know anything about that. If it's a Swapchain depth format, we'll use the one that's passed in because again, we don't know what that is at the moment. We'll defer commitment. Swapchain depth format. Let's make this a bit more readable. All right. What's wrong? What's it complaining about? And, oh, that's wrong. If it's a particular format, like a Vulkan format, we can just use that, which is the best case. Oh, I'm glad. I'm glad. Really, I was a bit worried, like, I don't understand necessarily why people watch programming streams. Find them a bit boring. Um, but I think my observation maybe or my hypothesis is that people like the vibe, you know? Like I saw this other streamer and it seemed like it was all about the vibe. People just hanging out with the vibe. So that's cool. It works for me. Right. Sample count is just going to come from here. This is pretty boring stuff. Doing a little bit of uh, bookkeeping. What we're doing is converting our structure into something that Vulkan can understand, which is relatively easy because we kind of stole Vulkan structure. So tell me, what time zone would you prefer? So I'm in Australia, so it's I'm running the stream in my morning, but I wasn't trying to figure out where the best time to stream is. Might play around a bit. Uh, yeah, yeah, cool. Well, this works. All right, that's good enough. Import that. Great. So, we have the render pass layout, and we are going to get the render pass attachments from that. This is just like the user declaring like, I want like 6 textures attached. I want I want to render to like 4 textures or whatever. Um, yeah. You know what? What's it called? Render doc. Should have recent captures. Should have a deferred capture. So this is what the attachments look like. So um, I would declare a depth attachment here. I'd declare a color attachment for rendering the textures too, just the like base light, the base color. I'd have what's this one for? I always get confused about these two. I'm pretty sure this one's maybe normal. No, I think this one's the world positions. Anyway, you've got a bunch of color attachments that you're rendering to, and then you combine them to form the final image. So that's what's happening here. We're creating like a little high-level interface to describe these attachments so that you can express that more easily. So render pass attachments, and then we're going to convert them using our conversion function. We're going to need the Swapchain color format and the Swapchain depth format to complete that conversion. And then we're going to need to convert that vector, that list to a vector, because that's what Vulkan asks for. Oh gosh, I can't imagine what that's like. Not sleeping for 2 weeks. That's crazy. Like, how does that feel? Let's make sure to get the Swapchain. And we're going to grab the depth format and the surface format from, so let depth format equal that, and color format, I'm going to use the American spelling. Oh man, that sucks. That's so hard. Yeah. Yeah, I can imagine it just makes everything worse. And that can be such a like, you get in like such a fragile state. Like, uh, yeah, I got burnt out a little while ago, from work and just like stress and stuff. And yeah, you just hit like this real low point. It's so hard to get yourself back up. Something like that would be like debilitating. I'm sure that's how you say it, but yeah. Oh gosh. I'm glad you're able to contact your GP. Yeah. Yeah, no, that seems wise. Maybe they can help kind of, like get you out of the like, ugh, the slump. Okay. What flavor of Australian? What does that mean? Like, where am I from? Um, yeah, so like I'm from like streaming from Perth. Streaming from Perth, so that's the flavor. But yeah. You can never hear your own accent, so hey, Luxan, thanks for joining. Why Haskell? That's a good question. So, uh, I really enjoy Haskell for the kind of expressive power that gives you. Um, I really like the ways I've been inspired by like papers and stuff that I read about the ways that they're using the properties of Haskell to create this very like readable, usable code. Uh, it's like they've got this high level description of something, and then and that's what the user can use. That's the interface to the library. But then on the back end, it's like very complicated, and all these things are happening, and it's making all these guarantees. But the interface is very simple, and usually what they're doing is they're making use of certain type classes. They're called, or um, I'll show you. Package. So yeah, there's like this branch of mathematics that studies it's like category theory, and it studies, or pure mathematics, it studies different types of it analyzes structures from an abstract perspective and tries to understand like what are the similarities between the structures, and like maybe this structure is made up of lots of different parts, and what are those parts. And so it's kind of this analysis of abstraction, really, like given a list and given an option type, like what is the similarity between those two things? What operations does a list support that a maybe or an optional type also supports? And like why is that the case? So it's a sort of study of these categories. And in Haskell, they're sort of implemented as, oh, okay. Oh, great, 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 great. Sorry. Oh my gosh, mansplaining there. Um, yeah, yeah. That's why. I just because I want to create a high level expressible interface for frame breakdowns, for like rendering stuff, and yeah, I want that to be easy to use because I want to experiment with like lots of different frame breakdown styles and that kind of thing, different ways of rendering a frame. Um, but I don't want to be dealing with like I don't want to be writing raw Vulkan from like uh yeah every time I try and do that. So I want to understand Vulkan, write a little engine for it, and then just have like a high level description of the rendering pipeline. That's the hope. That's the dream. I did. I did. In fact, that's what you can see on the right here. So before I did this project, I started with just like, so this is rendering a triangle. So we load the shaders, we create, these are just raw calls to Vulkan's, like to the Haskell Vulkan API, vert shader, fragment shader. Then we create the pipeline stages, we create the pipeline, create frames to render to, or we create synchronization primitives for the frames, we create the command pool, uh, and so on and so on and so on. And 444 lines later, just for a triangle. Um, are you only into Vulkan? Do you mean like, am I also into OpenGL and stuff? But yeah, anyway, I ended up making like a bunch of these, just raw ones. Like I got a deferred rendering one, and yeah, just things got out of hand a little bit. And then I'd forget things, like I'd forget how certain things work and what order to call things in, and I was like, I'm a bit over this. So I gave it a try, like abstracting like a little bit, like not abstracting a lot. And then I was like, this is good and working. Um, let's make a stream about it. Just get myself out there. Uh, so am I only into Vulkan? Um, I've learned OpenGL at uni, and we made a few games with it. Uh, and the concepts about that I see explained in these frame breakdowns, they seem to map a lot easier to Vulkan than OpenGL. So I'm just gonna start with Vulkan. And because I've already spent some time learning it, I probably have a better understanding of Vulkan now than OpenGL. So, okay, that's difficult. Yeah, yeah, like this project wouldn't be possible without like the Vulkan library for Haskell. I studied computer science and it was like games technology and no, it's computer science and games technology. So I had like a, it's like, I don't know what they called. Like there's like a major and there's two streams. There's like computer science and then there's games technology, which is basically just computer science plus OpenGL. So, it's 3 years worth of units, but that's basically it. So yeah, there's some auto-generated bindings for Vulkan, which is great because I mean they're not amazing, but it's great because you can get access to everything without having to hit C. Oh no, it's totally fine. Like I love people asking questions. It's great. Um, yeah, no, it's really good. Please feel free to ask many questions and related or not related. I'm totally happy. Right, render pass. So yeah, like we're not trying to abstract too much here. Like that's something that's worth mentioning is like we're just trying to like get some of the more awful parts out. So like you can see here, I've got this like render types function. It's sort of like the high level description of stuff. And I'm literally just like using Vulkan types and stuff. I'm not trying to abstract too much. Um, what I want to abstract is like the correct call order for things and memory allocation and all that kind of stuff because I just want to learn that stuff once, implement it, and then leave it be. So render passes, sub passes. And we're gonna try and like iterate on this. So we'll make something like really dumb and then we'll like weekly we'll iterate on it, make it better. Render pass, sub passes, render pass layout. Great. What else do we need? And got subpass descriptions, made subpass dependencies. Great. Okay, so we made the render pass create info. Then we're going to say with render pass Just gonna pass that create info on. What's your PhD in? Let's not compare brain sizes here. It's impossible to measure. It's true. That's not, yeah, that's the thing. Like, I would call myself, I was gonna say, like, this isn't about, like, something that I found is, like, I'm not super intelligent. It's like, there are people that are a lot more intelligent than me. Like, they're really good at picking things up quickly and things like that. And I take, like, ages and ages and ages. But, like, it's just sort of like hard work. I was gonna say that, but then I was like, you know what? That's not necessarily true. It's like, it's hard work, and then also, like, you're not sick, and you're not tired, and you're not burnt out, and you're not stressed, and all this other kind of stuff. So, yeah. Okay, we're just gonna wrap this Vulkan call in our little resource thing that we made earlier. Yeah, oh, it's totally valid. And it's an important skill set. And then like learning things from scratch is like thing on top. Like most of work isn't actually doing things from scratch. So oh, math and computer graphics. That's really cool. That's really interesting. Like how do they relate? How do math and computer graphics relate in a PhD? Excuse me. Cool. So made a random pass for each pipeline. Okay, okay. Yeah, it's true. They do relate a lot. I mean, it's all computer graphics, it's all math. But yeah, just wondering in that specific example, because there lot like there's just lots of different ways to approach it. Um, all right. Well, it really sucks because you guys just come on and it's been guys and girls have just come on and it's been great to chat to you. But I've got to go. And my brain is falling apart. So yeah, I'm gonna end the stream here, and we'll be back. I'll update the stream schedule about when I'll be back. Um, and yeah, I'll see you guys again. And I'll do a little bit of planning about what to do next. Yeah, it's true. Most people are web developers. Yeah. Even me, like most of the stuff I've been doing is in web. Even when we are doing Haskell, it's like writing backend servers for web. I feel like it's just where the money's at. But yeah, it's great to have you guys on. I really appreciate you guys chatting and following the stream and stuff. So I'll be uploading this stream in full to my YouTube channel, SamBNT_TV. So you can watch the first part of the stream and this part. And over time, hopefully, I'll upload some videos on specific concepts and stuff. Uh, but yeah, it was great to have you guys and girls and everyone. All right, have a good weekend. See ya.